Hello everyone, the title of our study is Ecological Dynamics and Equilibrium Analysis of Predator and Prey Model and the Influence of Infectious Disease. Predator-prey model is one of the classic models used to describe population interactions in ecology. In the traditional Leslie-Gore models, the interaction between predator and prey is simplified to the growth of prey and predator's feeding behavior. However, in real ecosystems, predator populations can be affected by infectious disease, which can significantly alter the dynamic properties of the population. Our project focuses on the stability of the Leslie-Gore predator-prey model when predators are affected by the SEIR infectious disease model. It aims to develop new mathematical models to analyze the stability of predator-prey system. In turn, it analyzes the overall effect of infectious disease in predators on the system. My presentation is divided into the following 4 parts. The first is modeling the system of equations, and the second is the analysis of the equilibrium point, and the second is the numerical stimulation, and the last is our discussion and conclusion. First, let's look at the establishment of the model equation system. Before the model construction, we make the following assumptions. First, the predator-prey relationship follows the classical Leslie-Gore model. Second, infectious disease are transmitted by contact in predator populations, and the rate of infection is related to the frequency of contact between individual predators. And finally, predators' ability to hunt is significantly reduced after infection with a disease. The specific model equations are shown on this page. The first equation is the dynamic of predator population, and the second equation is the dynamic of the susceptible predator population, and the third equation is the dynamic of the exposed predator population, and the fourth equation describes the dynamic of the infected predator population. The fifth equation describes the dynamic of removed predator population. When t equals to 0, the populations of susceptible, exposed, infected, and removed predators are denoted as S0, E0, I0, and R0, respectively, and the population size of the prey as X0, as initial conditions of the system of differential equations. In order to simplify the analytical process of the model, the original predator-prey model was dimensionless. At the same time, new dimensionless parameters are introduced. Based on the above variable substitutions, and the original predator-prey model can be represented in the dimensionless form. In order to discretize the dimensionless model, the continuous time model is converted to a discrete time model by using the forward ruler methods. Let the time step be delta t, and the time point be tn equals to n delta t. Then the discretized model equations are shown as follows. Now is the second part, the equilibrium point analysis. First, we need to solve for the equilibrium points. In order to determine all the equilibrium points of the model, the system of equations after discretizations needs to be solved. The system of the equations has 3 equilibrium points, E0, E1, and E2. Here we focus on the stability of the E2 equilibrium point. The Jacobi matrix is a linearized approximation of the model in the velocity of the E2 point, and its elements are the partial derivatives of each equations in the model with respect to all variables. Reasonable values are assigned to the parameters involved in the equations. The eigenvalues of the Ball-Jacobi matrix were solved using Python software, and 5 eigenvalues were obtained as follows. Next, look at the third part, numerical stimulation. By plotting the time series of the system, it is possible to show the change in the number of predator samples during the selection of generalizations and observe the presence of the periodic behavior or other dynamic features. The predation rate and disease transmission case are all important parameters. Bifurcation diagrams shows the state change in the system when varying the predation rate. The gentle tendency of the system state to change with predation rate suggests that the parameters' effect on the overall state of the system is gradual and does not immediately trigger unstable dynamic behavior. Finally, let's look at the fourth part, the conclusion and discussion of our study. Although the predator pre-infectious disease model proposed in this paper can describe the dynamic relationship between predator and prey to a certain extent, it still has the following limitations in real ecosystems. First, it ignores the influence of environmental factors. Secondly, the spatial heterogeneity of predator population was ignored. And thirdly, that the model may be not applicable to ecosystems with complex food webs or multiple predator-prey relationships. To enhance the model, we can introduce the time-varying parameters and consider spatial extension. Also, we can refer to the complex food web model for extension. In summary, this paper investigates the dynamic behavior and stability of the predator-prey system under the influence of the SEIR model. The numerical stimulation results show a higher conversion rate, accelerates the infection process of predators, lead to drastic fluctuations in the population size, while increasing the recovery rate of predators help the system tend to equilibrium. This concludes my report. Thanks for your listening.